Okay, oxidation and reduction really comes into play when we deal with voltaic cells. So what it is either called a galvanic cell or an electrochemical cell or a voltaic cell, so many different words for it. And it's a device that converts chemical energy into electrical energy. And this occurs with redox reactions. The most common use, you I'm sure can expect, would be batteries. The two main components of a voltaic cell. First, we're going to have two solid metals, for instance copper and zinc, and each metal is placed in a solution that contains its ions, like copper sulfate and zinc sulfate. Each solution will have a slight charge because an equilibrium will be established. So we have Cu solid in equilibrium with copper 2+ ions and 2 extra electrons. The more reactive a metal, the further the reaction goes to the product. When a circuit is set up between the two metals, the electric potential may be determined. It's often what we think of when we're dealing with power. So, looking at the specifics, the more reactive metal, so looking back at what we did yesterday in the lab, in the web lab, and the day before in notes, the more reactive a metal is, the more it will be the negative electrode. It's going to be losing those electrons. And this we know is an oxidation reaction. So at the negative electrode, we're losing electrons, that's why it's negative, and that's an oxidation reaction. We also call this, more specifically when dealing with voltaic cells, we call it the anode. So oxidation occurs at the anode. In an example, we have zinc solid forming Zn2+ plus 2 electrons. The less reactive metal is going to be the positive electrode, and that's because it is gaining electrons. And we have reduction taking place whenever we gain electrons, and we call this the cathode. So we have Cu2+ from the aqueous solution. Electrons are going towards that, and so more copper solid, that solid metal, is going to be occurring. We call that the cathode. So you can imagine the cathode is going to be getting bigger because we're adding to the amount of copper that's there. Okay, let's take a look at this reaction. We want to first ask ourselves which is being oxidized and therefore which is being reduced. So we can take a look at their oxidation numbers. Magnesium's all on its own here, so we know that's a 0. The chlorine, Cl2, is all on its own, so that is a 0. And then chlorine we know is always a -1, and magnesium's oxidation number is always a +2, which makes sense because if this is a -1 and there's 2 of them, we have a -2. And remember, overall, we're always going to have a 0 charge on a compound. So we're going with magnesium from 0 to a 2+. That means that it is being oxidized. With the chlorine, we're going from a 0 to a 1-, so that is what's being reduced. Okay, what element then serves as the anode? We said that's where the oxidation occurs, so the magnesium is our anode, and therefore the cathode would be chlorine. Okay, 2 missing items. Voltmeter. It measures the potential difference between those 2 electrodes. And we know we also need a salt bridge, and that goes between the 2 different solutions. It's a place for movement of ions between the solution, and it's what truly completes the circuit. it maintains our electric neutrality. So let's take a look. This is what a common voltaic cell would look like if we're not dealing with a battery, if we're just looking at solutions. I have some copper here in a solution of copper sulfate. This we can see is going, electrons are going into it, into the solution. This is my cathode, it's being reduced. Gaining electrons, being reduced. So we have Cu2 plus 2 electrons forming Cu solid. The cathode is the positive electrode. Here in between is my voltmeter, measuring my current. And I have electrons going from the anode to the cathode. That's why I have these electrons that are able to pop off. So we can draw in my electrodes. The zinc then is my anode because it is oxidized. And it is my negative electrode. And I have my half reaction for this of Zn going to Zn2 plus 2 electrons. You can see that we have sulfate ions coming into this solution, and we have sodium ions reacting with the sulfate ions in this solution, so that we never have too much of anything in any of them. They just keep reacting so that I have an equal number of ions as I'm doing this transfer throughout. Also, we can notice, since my salt bridge is here, that my cations go towards my cathode, and my anions, in this case the SO42 negative, go towards my anode.